Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Venus, our nearest planetary neighbor, hides a meteorological nightmare beneath its serene, cloud-wrapped exterior. From Earth, this bright wanderer appears as a peaceful beacon in our night sky, but the reality couldn't be more different. Venus presents perhaps the most extreme weather system in our solar system, a world where the concepts of weather and climate take on alien dimensions that challenge our terrestrial understanding. Approaching Venus, one first encounters its mesmerizing cloud deck, hovering 50 to 70 kilometers above the scorched surface. These aren't the water clouds we know on Earth. Venus's clouds consist primarily of sulfuric acid droplets, creating a highly reflective veil that returns about 70% of incoming sunlight back to space. This reflectivity explains why Venus appears so brilliant from Earth, outshining everything in our night sky except the moon. Yet beneath this shimmering exterior lies a planetary climate system gone catastrophically wrong. The atmosphere of Venus is 96% carbon dioxide, creating the most extreme greenhouse effect in our solar system. Surface temperatures reach 475 degrees Celsius, hot enough to melt lead and zinc. The atmospheric pressure at ground level crushes at 92 times Earth's sea level pressure, equivalent to being 900 meters deep in Earth's oceans. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe, it's free, and it helps us grow this community together. The story of Venusian weather begins with its peculiar rotation. Venus spins backward compared to most planets, with its day lasting longer than its year. A single Venusian day stretches for 243 Earth days, while it orbits the Sun in just 225 Earth days. This means that on Venus, the Sun rises in the west and sets in the east, taking 117 Earth days to cross the sky. This slow rotation profoundly influences atmospheric circulation. On Earth, our 24-hour day creates complex weather patterns as different regions heat and cool. On Venus, the extended day-night cycle should theoretically create massive temperature differences between the day and night sides, driving catastrophic storms. Yet something strange happens. Instead, despite receiving twice the solar radiation as Earth and having day-night cycles that last for months, Venus shows remarkably little temperature variation across its surface. This paradox intrigued planetary scientists after the first successful Soviet Venera missions in the 1960s and 70s. How could a planet with such extreme conditions maintain such uniform temperatures? The answer lies in Venus's superrotation, perhaps the most bizarre meteorological phenomenon in our planetary neighborhood. While Venus itself rotates extremely slowly, its atmosphere moves at tremendous speeds. High-altitude winds circle the planet in just 4 Earth days, creating winds that reach 360 kilometers per hour. This means the atmosphere circles Venus 60 times faster than the planet rotates, a situation without parallel anywhere else in our solar system. These winds distribute heat so efficiently that there's virtually no temperature difference between day and night sides, or between equator and poles, a stark contrast to Earth's varied climate zones. In essence, Venus's atmosphere acts as a global heat distribution system of extraordinary efficiency, but the mechanisms driving this super-rotation remained mysterious until relatively recently. The key to understanding Venus's weather begins with its unique cloud structure, a 3-tiered system that extends from approximately 48 to 70 kilometers above the surface. These aren't scattered clouds as we see on Earth, but rather a continuous global envelope shrouding the entire planet. The cloud system consists of 3 distinct layers. The uppermost layer, extending from about 60 to 70 kilometers, features fine sulfuric acid mist, with particles less than 1 micrometer in diameter. The middle layer, from 52 to 60 kilometers, contains slightly larger droplets. The lower layer, reaching down to 48 kilometers, holds the largest particles. Below 48 kilometers, the atmosphere becomes relatively clear, though still incredibly dense by Earth standards. This layered cloud structure creates fascinating phenomena that challenge our understanding of atmospheric physics. The planet's upper atmosphere undergoes curious transitions that weren't properly documented until relatively recently. The European Space Agency's Venus Express orbiter, which studied Venus from 2006 to 2014, discovered something extraordinary. The cloud patterns at the top of Venus's atmosphere seem to change dramatically over time. When ultraviolet light strikes the upper clouds, it interacts with unknown absorbers, possibly sulfur-bearing compounds, creating the distinctive yellowish appearance and dark streaks visible from space. These absorbers create a complex pattern of bright and dark regions when viewed in ultraviolet light, forming a striking V shape that rotates around the planet every 4 to 5 Earth days. Even more puzzling is how these cloud patterns have changed over decades. Images from the Mariner 10 mission in the 1970s showed markedly different cloud features than those observed by Venus Express in the early 21st century. This suggests that Venus's atmospheric circulation patterns may undergo long-term variations, perhaps even climate change on a planetary scale. Below the clouds, conditions become increasingly hostile, as pressure and temperature rise exponentially. With decreasing altitude, the lower atmosphere takes on properties more like those of an ocean than air. At the surface, carbon dioxide becomes so dense it behaves as a supercritical fluid rather than a gas, a state where the distinction between liquid and gas effectively disappears. This supercritical condition creates an environment where weather works utterly differently than on Earth. Near the surface, winds move excruciatingly slowly, just a few kilometers per hour, but carry tremendous force due to the extreme density of the atmosphere. It would feel like trying to move through honey rather than air, and even gentle breezes would hit with the force of sledgehammers. Evidence from Soviet Venera landers, which survived briefly on Venus's surface in the 1970s and 80s, revealed another surprise. Light at the surface appears oddly diffused, creating an eerie orange-red glow. This lighting effect, combined with the crushing pressure and searing heat, makes Venus's surface perhaps the closest natural approximation to traditional conceptions of hell in our solar system. Despite these extreme conditions, the atmosphere isn't static. Venus experiences its own unique form of precipitation, but not raindrops as we know them. In the cooler upper atmosphere, sulfuric acid can fall as rain, but it evaporates long before reaching the surface due to the increasing temperatures below. In the lower, searingly hot regions, minerals like iron chloride might precipitate, creating metal snow that settles on mountaintops. Venus's atmosphere operates as a single massive heat engine, unlike anything seen on Earth. While Earth's weather is driven primarily by the temperature difference between equator and poles, Venus's weather machine runs on the temperature gradient between its upper atmosphere and surface. The process begins with sunlight striking the cloud tops. The upper clouds reflect most of this energy back to space, but some penetrates deeper, creating a greenhouse effect of staggering proportion. This trapped heat warms the lower atmosphere and surface to temperatures hot enough to glow dull red in complete darkness. This extreme heating creates a phenomenon known as a Hadley cell, but on a planetary scale that dwarfs Earth's equivalent weather structures. On Venus, heated air rises from the equatorial region all the way to the poles in vast convection currents. As this air cools at higher altitudes, it flows back toward the equator, completing a cycle that efficiently distributes heat across the entire planet. The Japan Aerospace Exploration Agency's Akatsuki orbiter, which arrived at Venus in 2015 after an initial failed orbital insertion 5 years earlier, has provided revolutionary insights into these circulation patterns. Akatsuki's infrared and ultraviolet cameras revealed unexpected cloud structure complexities, including massive bow-shaped wave patterns stretching 4,000 kilometers across the cloud tops. These atmospheric gravity waves, as scientists call them, appear stationary relative to Venus's surface features below, despite existing in an atmosphere moving at hundreds of kilometers per hour. This suggests a direct connection between surface topography and upper atmospheric dynamics, previously thought impossible given the extreme thickness of Venus's atmosphere. Perhaps most intriguing is Venus's atmospheric polar vortex, a swirling, massive clouds centered on each pole that forms a distinctive double-eye structure. Unlike Earth's polar vortices, which typically maintain relatively stable positions over the poles, Venus's southern polar vortex has been observed changing shape rapidly, sometimes in just 24 hours, morphing from a double-eye formation to a single core and back again. These polar structures represent another puzzle in Venus's complex atmospheric system. The vortices appear to rotate around a central point while simultaneously changing shape, sometimes forming perfect dipole configurations and other times breaking into irregular patterns. The mechanisms driving these transformations remain poorly understood, though they likely involve complex interactions between the planet's slow rotation and its super-rotating atmosphere. Venus also experiences something akin to seasons, despite its nearly circular orbit and minimal axial tilt. These aren't seasons in the Earth sense, but rather atmospheric variations driven by the solar tide, the gravitational influence of the Sun on Venus's thick atmosphere. As Venus orbits the Sun, subtle shifts occur in atmospheric circulation patterns, creating cyclical changes in cloud patterns visible from Earth. The planet's weather is further complicated by mysterious hotspots that appear in the cloud layer over certain surface features, suggesting that Venus's geology might influence its atmosphere more than previously thought. Mountain ranges like Maxwell Montes appear to disrupt atmospheric circulation patterns, creating standing waves in the airflow that extend all the way to the cloud tops, 70 kilometers above the surface. For decades, one of the most controversial questions about Venus's atmosphere was whether it could generate lightning. Earth's lightning forms through charge separation in water-laden clouds. But Venus lacks water clouds entirely. Yet multiple spacecraft, from the Soviet Venera probes to NASA's Pioneer Venus orbiter, detected radio emissions consistent with lightning discharges. The mystery deepened when the European Space Agency's Venus Express orbiter failed to detect the expected Whistler waves, electromagnetic pulses that travel along magnetic field lines that should accompany lightning strikes. This created a scientific puzzle. Was Venus experiencing lightning-like discharges through an entirely different mechanism than Earth? Recent analysis suggests Venus indeed hosts electrical storms, but with crucial differences from terrestrial lightning. On Earth, most lightning occurs within clouds or between clouds and the ground. On Venus, discharges likely occur between different cloud layers or between the clouds and the ionosphere, the electrically charged upper region of the atmosphere. What makes Venusian lightning particularly fascinating is its potential chemical impact. Lightning strikes in Venus's carbon dioxide and sulfur-rich atmosphere would create complex chemical reactions, potentially forming carbon monoxide and sulfur oxides. This atmospheric chemistry could explain some of the unusual compounds detected in trace amounts in Venus's clouds, including the mysterious ultraviolet-absorbing substances that create the planet's distinctive cloud patterns. The planet's extreme surface conditions create another meteorological curiosity. The boundary between atmosphere and surface behaves radically differently than on Earth. The atmosphere is so dense at the surface that it interacts with the landscape more like a fluid than a gas. This creates phenomena where airflow around mountains generates pressure differences that can lift and transport surface material, a process more akin to underwater currents than wind as we understand it. Perhaps the most extreme weather on Venus occurs in its deepest valleys. In these low-lying regions, the already crushing atmospheric pressure increases even further, and temperatures climb to their highest values. The Soviet Venera 14 lander, which touched down in a relatively flat region in 1982, measured temperatures of 467 degrees Celsius. In the deepest parts of rift valleys like Diana Chasma, temperatures could potentially exceed 500 degrees, conditions where the atmosphere begins to interact chemically with surface rocks in a process of continuous, slow-motion weathering. This weathering creates another uniquely Venusian phenomenon, chemical snow on mountaintops. Venus's highlands rise above the densest part of the atmosphere, creating slightly cooler conditions. Here, minerals in the atmosphere, particularly compounds containing lead and bismuth, can condense and coat the mountain peaks with a metallic frost. Evidence for this came from the Pioneer Venus radar mapper, which discovered that Venus's highest mountains are highly reflective to radar, consistent with a metal coating. The complex interplay between surface and atmosphere continues with Venus's mysterious highland haze. Observations from Earth-based telescopes and space probes indicate that the air above Venus's mountains contains different aerosols than the surrounding regions, creating localized weather patterns tied directly to the landscape below. Despite being separated by dozens of kilometers of sulfuric acid clouds, Venus's current hellish conditions may not have always existed. Mounting evidence suggests Venus once had conditions potentially similar to early Earth, with possible shallow oceans and moderate temperatures. What transformed this world into its current state represents one of the most dramatic climate changes imaginable. The transformation likely began with Venus's slightly closer orbit to the Sun. Receiving approximately 40% more solar radiation than Earth, Venus would have experienced stronger evaporation of any surface water. Water vapor is a powerful greenhouse gas, and as more entered the atmosphere, temperatures would have gradually increased in a positive feedback loop. As temperatures rose, more water vapor entered the atmosphere, trapping more heat, raising temperatures further in a runaway greenhouse effect. Eventually, water molecules in the upper atmosphere would have been split by ultraviolet radiation, with the hydrogen escaping to space and the oxygen binding with surface materials, without water to facilitate carbon recycling through plate tectonics. Volcanic carbon dioxide accumulated unchecked in the atmosphere. This catastrophic process likely occurred within the first billion years of the planet's existence. Today, Venus has less than 1/10,000th the amount of water as Earth, primarily existing as trace atmospheric hydrogen sulfide and sulfuric acid. What makes this history particularly relevant is the possibility that Venus experiences ongoing cycles of atmospheric change, albeit less dramatic than its original transformation. The planet's sulfur cycle appears especially dynamic. Observations from multiple missions indicate that the concentration of sulfur dioxide in Venus's upper atmosphere fluctuates significantly over periods of years to decades. These fluctuations could result from several processes. Large-scale volcanic eruptions might inject massive amounts of sulfur dioxide into the atmosphere. Alternatively, changes in atmospheric circulation patterns could transport more sulfur-rich air from lower altitudes to the cloud tops. A third possibility involves complex photochemical reactions that create periodic changes in how sulfur compounds are distributed throughout the atmosphere. The implications extend beyond Venus itself. Understanding these processes provides insight into extreme climate states that could theoretically affect other worlds, including Earth under different conditions. Venus serves as a cautionary example of how a planetary climate system can cross critical thresholds into dramatically different states. Recent observations have revealed another mysterious weather phenomenon, a massive, planet-wide bow-shaped structure that appears to remain stationary even as the atmosphere around it rotates at high speed. First observed by Japan's Akatsuki spacecraft in 2015, this feature spans Venus's southern hemisphere and appears to be a standing atmospheric gravity wave tied to surface topography, specifically the mountainous region called Aphrodite. Terra, its existence challenges our understanding of how Venus's atmosphere works. Computer models suggest such a feature should be torn apart by the super-rotating winds, yet it persists. The most likely explanation involves complex interactions between surface topography, atmospheric circulation, and the planet's slow rotation, creating resonant wave patterns that can maintain their structure despite the chaotically fast winds. Further complicating the picture is evidence of longer-term changes. Comparative analysis of ultraviolet images from missions spanning 4 decades, from Mariner 10 in 1974 to Venus Express in 2014, shows significant changes in the distribution and patterns of the unknown ultraviolet absorber in Venus's clouds. While Venus remains one of the most hostile environments in our solar system, recent missions have begun unraveling its atmospheric secrets through increasingly sophisticated remote sensing. The European Space Agency's Venus Express mission revolutionized our understanding of the planet's atmospheric dynamics through its Venus monitoring camera and visible and infrared thermal imaging spectrometer. These instruments tracked cloud movements at different altitudes, revealing that Venus's atmospheric superrotation isn't uniform. Wind speeds vary dramatically with altitude, starting at just a few kilometers per hour at the surface, increasing to around 60 kilometers per hour at cloud base level, and reaching speeds of 360 kilometers per hour at the cloud tops. This vertical wind shear creates complex turbulence patterns that transfer momentum between atmospheric layers. Even more surprisingly, Venus Express discovered that these wind patterns shift over time. The highest altitude winds showed variations of up to 20% in speed over the mission's 8-year duration. These fluctuations don't appear to follow any simple pattern related to Venus's day-night cycle or orbital position, suggesting the existence of complex long-term weather cycles operating within the Venusian atmosphere. Japan's Akatsuki mission, currently the only operational spacecraft at Venus, builds on these discoveries with specialized cameras designed specifically to observe different atmospheric layers. Its mid-infrared camera can peer through the clouds to observe the lower atmosphere, while its ultraviolet imager tracks the mysterious absorbing chemicals in the upper clouds. One of Akatsuki's most significant findings involved massive streak-like cloud patterns stretching 10,000 kilometers, features dubbed planetary scale streaks. These structures align in the east-west direction and persist for days despite the rapid atmospheric rotation. Their origin remains debated, though they likely result from interactions between the planet's topography and atmospheric circulation. Perhaps most puzzling of Venus's polar atmospheric dynamics. Both poles exhibit complex vortex structures, but they don't mirror each other as might be expected. The northern polar vortex typically maintains a more stable configuration, while the southern vortex undergoes dramatic morphological changes over periods as short as 24 hours. These polar vortices also exhibit unexpected temperature patterns. Counterintuitively, Venus's poles are warmer than expected given the reduced solar heating at high latitudes. This suggests that the planet's atmospheric circulation efficiently transports heat from equatorial regions poleward, unlike Earth, where polar regions remain significantly colder than the tropics. Recent observation campaigns have also identified a previously unknown atmospheric layer at around 85 kilometers altitude. This transition region between the main cloud deck and the thermosphere exhibits unexpected temperature inversions and chemical compositions that don't match predictions from atmospheric models. Another recent discovery concerns Venus's mysterious polar cold collar, a ring of cooler air that surrounds each polar vortex. These features appear as dark bands in infrared observations and maintain temperatures 15 to 40 degrees Celsius cooler than surrounding regions. Their persistence suggests complex interactions between radiative heating, atmospheric chemistry, and dynamics that remain poorly understood. The study of Venus's weather continues unveiling surprises. In 2018, researchers analyzing Venus Express data discovered evidence for something previously thought impossible: relatively thin zones in Venus's dense atmosphere. These regions exhibit atmospheric pressure about 20%, lower than surrounding areas at the same altitude, creating atmospheric holes that appear to form and dissipate over periods of days to weeks. As our understanding of Venus's complex weather systems grows, so too does our technological capability to explore this hostile world. The next decade promises breakthrough missions that will revolutionize our knowledge of Earth's twisted sister planet. NASA's Da Vinci Plus, Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging Plus mission, scheduled to launch in 2029, will deploy a sophisticated descent probe equipped with a suite of instruments designed to analyze the atmosphere during its hour-long journey to the surface. This mission represents the first American attempt to enter Venus's atmosphere since the Pioneer Venus multiprobe in 1978. The Da Vinci Plus probe will measure atmospheric composition at different altitudes with unprecedented precision, potentially resolving debates about trace gas concentrations, including the controversial detection of phosphine announced in 2020, a gas that on Earth is primarily produced by biological processes. As it descends, The probe will capture high-resolution images of the surface's tessera regions, heavily deformed highlands that may hold clues to Venus's earlier history. Complementing Da Vinci Plus, NASA's Veritas, Venus Emissivity, Radio Science, INSAR Topography and Spectroscopy mission will use cutting-edge radar technologies to create the most detailed maps of Venus's surface ever obtained. Though focused primarily on geology, Veritas will contribute to atmospheric science by precisely measuring minute variations in Venus's gravitational field caused by atmospheric density changes. The European Space Agency plans its own Venus mission, named Envision, featuring a synthetic aperture radar to map surface changes since NASA's Magellan mission in the 1990s. Envision will also carry a suite of spectrometers to study atmospheric composition and surface-atmosphere interactions, particularly focusing on whether active volcanism continues to inject new gases into Venus's chemical cauldron. India has announced plans for Shukrayan-1, a Venus orbiter focusing on atmospheric chemistry. Earth's instruments will specifically target the mysterious ultraviolet absorber in Venus's clouds that creates the distinctive dark patches visible in UV light. Identifying this substance would resolve one of the longest-standing mysteries in planetary science. Russia and the United States have discussed a potential joint mission called Venera D, combining an orbiter, lander, and possibly long-duration aerial platforms, balloons designed to float in Venus's upper cloud layer, where temperatures and pressures are similar to Earth's surface. These balloons could revolutionize Venus meteorology by providing in situ measurements of cloud properties, wind patterns, and chemical processes over weeks or months. Private ventures are also eyeing Venus. Several companies have proposed small, specialized missions focusing on atmospheric research, including microprobes that could study cloud particles in detail or deploy swarms of tiny sensors to track atmospheric circulation patterns in real time. Beyond these planned missions, Venus atmospheric scientists dream of more ambitious projects. Networks of long-duration surface stations that could survive the extreme conditions long enough to detect weather variations, high-altitude research, platforms that would float in the habitable zone of Venus's atmosphere for years, and sample return missions that could bring Venusian cloud particles back to Earth for detailed laboratory analysis. Venus's extreme weather systems provide a crucial test for our understanding of how atmospheres work under conditions wildly different from Earth's. Studying Venus helps scientists refine climate models applicable to Earth and thousands of exoplanets discovered around other stars. The lessons learned from Venus's runaway greenhouse effect inform our understanding of climate change processes on our own planet. As these missions unfold over the coming decades, they promise to transform Venus from a mysterious, cloud-shrouded world into a laboratory for understanding extreme atmospheric physics. In doing so, they will help answer one of the most profound questions in planetary science. How did two planets that likely formed under similar conditions, Earth and Venus, evolve into such dramatically different worlds?